clustering, and we explained what clustering is. Basically, grouping similar objects together after we plot them into space, so they kind of look like dots or objects in space, and we combine similar objects together in a cluster. We have seen two different clustering methods. We mentioned two different clustering methods. One was the divisive clustering, which is what we have seen example of k-means, and with that type of clustering, we each point belongs to exactly one cluster. And the other type that we mentioned is the hierarchical clustering, which takes a different approach. So each point can belong to more than one cluster at a time, so there are overlaps. As you can see, these 2 points are together, and then we have that other cluster that includes these 2 and a third point. So they could overlap with this method. Why would we want to do something like that? So the last time we mentioned, with this hierarchical clustering, we will start where each point is considered a single cluster by itself, and start merging them together. And this is called a bottom-up approach. And so we start merging them until all of them are merged together into one big cluster. We do have another approach called top-down, which is what we will talk about next time, where we start with that big cluster where all of them are together and start separating them. So an example of that is the TV tree, and that's what we're going to see next time. So today, with the hierarchical clustering, we will we're going to see an example of that in the second half of the class, but the basic idea is we measure the distance between all the points, just like we did the last time, and the 2 points that are closest to each other, we merge them together first. And the same information can be recorded in a dendrogram. So the dendrogram will show the distance at which the points were merged, and which points were merged at that distance. So the first points that were merged is 1 and 3 at a distance 0.5. Next were merged points 2 and 5 at a distance 0.8. These 2. 3. The number 4 was added to this cluster. Now, once the points 2 and 5 are merged together, this is considered now one whole thing. We don't look at 2 and 5 separately anymore. This is a new cluster now that contains 2 and 5 in it. So we're going to add to that cluster another point, the point 4, and step 3. So at distance 3, which is 0.17, the point 4 was merged with this cluster. And so on, the dendrogram will show us which points were merged into which clusters at what distance. Eventually, all of them get merged together like this into one big cluster. That's step 5. So the last time we asked the question, why would we want, since we're looking for clusters or groups of similar points, why would we want to merge all of them into one big cluster like that? So the last time we asked this question, does anybody remember what was the answer to that? they stay like that. But here, they are overlapping, and eventually all of them end up into one big cluster. Why would we want to do something like that? Do you guys remember? So the idea here is that we have this dendrogram that shows us at which distance each of the points were merged, or each of the clusters were merged. And once we build this dendrogram for the whole, until we merge everything together at the end, we have the information about all the clusters and all the distances in between them at what distance they were merged, but this is not the final step of this algorithm. This is just an intermediate step that allows us to determine if there is a huge jump in distances. Let's say from here to here, it's a big jump. And if we see such a big jump, we should probably stop clustering at that point. So these clusters will be created, this one and that one, and then we'll stop. Because if we were to merge this cluster with that one, they are actually very far away from each other, and it might not logically make sense to say that they're similar, because there's a big distance between them. So we're going to monitor for jumps of big distances as we proceed through the end and say, okay, that's a good cluster, that's a good cluster. That one is not so good because there's a huge difference. So we're going to stop here and not merge this one with that one.
One question. The distance function in this case is the same as what we saw last time, like x2 minus x1, y2 minus y1?
We could use that. So the last time we have seen a version of the Euclidean distance, which was called Manhattan distance or city block distance. We could use that to calculate the distance between these points. We could use Euclidean distance or some other function that we want to define if these are, let's say, binary attributes or categorical attributes or some other attributes. The tricky part here with this algorithm is, yes, we could use the same function as we did with k-means to calculate the initial distances from one point to another. The question is, with k-means, we had a center, and always, once the points are added to some cluster, we always calculated the distance from the point to the center of the cluster, right, by taking the average of all the points. Now we don't have that situation anymore. There's no center here. So we need some formula to define what would be the distance from this cluster to that cluster. So if we wanted to merge, now these two are together, we consider them as one. Well, what's the distance from that new cluster to that one, or to this point all the way up here? We could take the average of these 2 points, or we could take the minimum distance from this cluster to that point by using the point that is closest here on the outside edge of this cluster. Or we could take the distance from the farthest away point to here. Or we could take the average of all the points. Or we could take the mean. So we need to decide what we're going to use for distances between these newly formed clusters. Because once we merge 1 and 3 together, this is now considered one whole thing. We're no longer looking at 1 separate and 3 separate. So what would be the distance now from all the other points to this newly formed whole thing called 1 and 3 together? So we need to specify the function that we're going to be using. And some differences from the k-means or from the divisive approaches is that with k-means we had k. K was the number of the clusters, and that was given to us before we start. In this case, we don't need to assume any particular number of clusters because we might end up with any number of clusters depending on the distances. So if there is a very large jump in distance from one cluster to another, we're going to stop there. What is inside the clusters? The semantics of the data. If we're to consider that, let's say this is the biological data about some animal, or it is financial data, or it's the data about producing cars. So whatever the meaning of the data is, the idea is we're grouping these points together because we want to find objects that are similar. Let's say these two animals are mammals, the others are birds. Or let's say these customers have a high risk of not paying their mortgage or their credit cards, the others are low risk. Or let's say for car manufacturing, this type of cars are sold better than the other type of cars. So we would logically create groups of objects that fit into specific description. Or we would first create the objects groups and then examine these groups to learn what kind of similar properties they have and what makes them to be together in the same group.